In this recording, I'm trying to talk a little bit about the shear and bending moment diagram, the qualitative method. So assume that such example, we have simply supported beam and distributed load triangle way. So first of all, we have to drive the reactions, and the best way would be calculation of sigma m around one of the points like A or C, and in case I prefer to go with point C, then from there I would be able to drive the reaction of point A. In that case, we have to concentrate on this part, which is distributed load. First, we have to convert it to the concentrated load, which, for example, for this case would be 20 multiplied by 5 divided by 2, which is the area of triangle. So for the other section here, as you see here, we have to convert it to the concentrated load and calculate 10 multiplied by 20 divided by 2. And the location of this load would be 1/3 from the epic, from the base, and 2/3 from the epic of point A. The same for this one. Assume that we are able to calculate and we reach to the point A. We're going to have AY equal to 83.33 kilonewton. We already did that and we saved the time. Then we do calculation of other reaction by sigma Fy. From there, we are able to drive Cy, which would be equal to 66.67 kilonewton. All right, now we have the reactions. It's very simple to do the procedure of calculation of drawing the shear first. So for calculation of shear diagram, we have to do is at the same level of location of the A and C, we're gonna draw the line, which is our beam, and we know this one is 83.33, and this one reaction is 66.67. When we start from the left side, which is essential, the load is upward, so we go upward up to the level of 83.33 kilonewton. Then after that, we have to know how much is the load. As you see, it's distributed load, and it's increasing because it starts from 0 and gonna reach to 20. In that case, when it's increasing, we have to go increasing for the shear diagram. So we have two options to draw something like this or like this, concave or convex. The best way is to draw a tangent to see is it incremental or decremental. It will be something like this, and as you see here, from the tangent to the horizontal line, the angle is keep increasing. If you see the theta 1 and theta 2, to compare them, you're going to see it's increasing. So that's what it's from the triangle distributed load from here. Then from there, we're going to see that it's decreasing from point B to point C. The amount, the intensity of load would be 20 kilonewton per meter, and it's going to reach to the 0, so it's decreased. For this case, the curvature would be something like this. As you see, if I draw a line horizontally and tangent, it's theta 1, and it's going to reach to theta 2. Theta 2 is much less than theta 1. It's decreasing. Now, and from here, we're going to have to, it's going upward. It's a positive 66.67, and we have to connect it to here. That's the shear diagram. Now, for calculation of bending moment diagram, we keep continue. And the point is how to calculate this area, which is A1 and A2. And in that case, at the point which we have zero shear, definitely we're going to have the maximum moment diagram. So it's good to know that we have the maximum moment here, and here you're going to see the shear from here to here is increasing as we talk about it here. So the same would be for the moment in belief, but in this case it's not. We should be careful about that, because whenever we are converting shear to the bending moment diagram, we have to deal with the absolute values of numericals you read. It's 83.33, which is positive in this case. It's reaching to the point 0. So what we have to do, we have to say that, okay, it's decreasing. If you remember, for the loading it was increasing, for the shear is decreasing. Because it's decreasing, the bending moment should be decreased as well, which we draw some curve like this. As you see, it's much more than this angle, so it's decreasing, and it's the maximum point, and we calculate the area for this one, and then we calculate, and we have no concentrated moment at the point A, so just the area, it would be point A1 at this point is the maximum, and then we're gonna see that it's changing from 0 to this point, which is whatever here is 66.67. And when we care about the comparing the values, 0 to absolute value is minus, is from 0 to absolute value of minus 66.67, which is positive. Absolute of this value is positive, so 0 to this value definitely is increasing, which is in contrast with this one. For the loading it was decreasing, so it's increasing, and I should draw a curve which is increasing, and the answer is like this. And we add A2 to this value, and we're gonna reach to 0. We have to reach to 0 because there is no moment at the pin support, as there were no moment at point A, which was roller support. So the important thing is that we have to know calculation of this area, which is application of table is important, and we have to know, are we eligible for this case to use table or not, which already have talked about it before. The next question is, is related to this load. 30 kilo keeps on the 2 kips per foot in such a pin. In that case, we assume that we do calculation of a reaction, and we derive the reaction. AY is equal to 26, and DY is equal to 24K. So very simple, we're gonna draw a line, shear diagram, and here we're gonna talk about bending moment diagram. AY is 26 and 24. So when it goes up, when it starts from left, it goes up to the level of 26. There is no other load. Keep continue. Then to the level of 30K, we have to go down because the load, we have the concentrated load. So 26 and 30 deducted, we're gonna reach to -4. We're going to keep continuing. There is no load between B and C. Now we're going to reach to point C. And at point C, we have distributed load. Whenever we have a distributed load, uniform load like this, intensity of 2K we have, for the calculation of shear, it will be changed to a linear line. So a straight line will be converted to linear line, and in that case, it would be something like this. Now, from here, we're going to know how much would be the value. 2 multiplied by 10 would be 20. We are in level of -4 here. -4 and 20 would be -24. Then we have 24 positive, so it would be this. So it would be a closed line, which shows that our calculation is correct. Then we are caring about the calculation of areas, area 1, area 2, area 3. Don't forget, we have to check, is there any other concentrated moment on the beam, because now we're talking about bending moment. Fortunately, we have no concentrated moment, so it starts from 0. It's a roller support, 0. Here is a pin support, 0. So from 0 we're going to start, we're going to reach to 0. At point A, the area would be start from 0. It's a straight line, so the bending moment should be linear, and we're going to draw a line here. And we're going to draw something like this, and this much, which is A1, which is a 26 multiplied by 6, and the value would be 156. Then after that, we have to add area number A2, which is the value would be 4 multiplied by 4, which is 16, but it's minus. Don't forget, it is minus and it's plus. So minus 16 plus 156, we're going to reach to 140. And it's a straight line, so it should be linear. Drop to 140. Then, for this case, from point C to point D, now it's linear, so we have to increase the order to the order number 2. It's order 1, it's y equal to ax, and plus c, it's order 1. Now, when we do the moment diagram, it's for the shear, and for the moment, y would be ax2 plus bx plus c. So it's from point C to point D. Now we want to know it's incremental or decremental. We have to use the absolute value. -4 absolute would be changed to -24 absolute, which we're going to say 4. It will be 24, so it means that it's increasing. Because it's increasing, the figure, the curve should be like this. As you see, the angle here is much less, so it's increasing. And it's trapezoidal, just we have to calculate this area and add this area to 140, -24 -4 divided by 2 multiplied by 10. And if we calculate, this one would be 140 minus, and minus 140 plus 140 gonna reach to the point 0. We're gonna go to the next example. Again, it's similar to the previous one, but we have the concentrated moment here. So what we can do is calculate the reactions. I assume that you are able to drive it, and I write just the reactions. 7.5, 72.5. Now I just draw the line exactly underneath this structure, shear diagram, then bending moment diagram, and from here it's upward, we go upward, the reaction we're gonna reach to the 67.5. Then we have distributed load, so it's a straight line. It would be a decline line, linear to the order 1, which is 15 multiplied by 6. When we multiply it with the 90, and it's 67.5. It shows that it would be added, but we have to show in this way. Straight line. Now we're gonna reach to this point, which is 90 minus would be added to 67.5, and after that we have no more concentrated load here from B to C, so we have to draw a straight line, and after that we have concentrated downward, so it goes down. How much? From here to here would be 50, whatever it is here. Then after that we have no load, we go straight. Whatever value you see here should be equal to 72.5, because when we reach to point D, we add 72.5, we have to reach to 0. It's a closed graph. So start from 0, reach to the point 0. Now it's very simple for calculation of moment, but don't forget we have one concentrated moment for this case. And we're gonna have A1, the calculation of this triangle, calculation of A2, A3, and A4. And we calculate based on geometry of each one. Here we're gonna have minus this much, and it's I have to write the numericals. The area is minus 217.5. For here it's here is minus 67.5, and here A1 is 151.9. In that case, it's linear. From 67.5 it's gonna reach to 0. It means that it's decreasing. So I need a sort of graph to show it's decreasing for the moment. Here. How much is here? It's the area here, whatever it is, which is 151.9. Then from here to here, from 0 to minus 16.9, it's increasing. So the graph should be incremental like this. We add this one. The point is that it's minus. So 151.9 plus minus 16.9. So it's going down, but incrementally goes down. We had another option to draw something like this, which is not correct. So it would be like incremental curve. And after that, we add A3, which is minus 67.5. And here we're gonna have, we have one concentrated moment, 150. So because it's you will see here it's clockwise, so it will be positive, it goes up. How much? 150, and we're gonna reach here to the value of 285. Then we decrease 67.5 because it's minus, it's a straight line, so it should be decline line, and we reach to point C. Now we are at point C, and the value is 217.5. From here to here is a straight line, so, and we have to add this value to this one, and we have to reach point D equal to 0. If not, there is something wrong with our calculation. So it would be like this. The last answer is 0. This one minus this area gonna reach to 0, and it proves that our calculation was correct. The next example is cantilever beam, and first we have to drive the reactions, which I assume that you can do it. It's very simple. The answer is 225, and we have a moment here 2700. It's the best is to draw the line underneath the structure as we talked before. So very simple, without wasting time, we can say it's upward. We're going upward. How much? 225. Then after that, from A to B, there is no load, so a straight line. Then it goes down. How much? 75. 75 minus 225, we're gonna reach to 150. From B to C, a straight line, no load in between. And after that, we have a straight distributed load, so it should be linear, and it should drop down because it's downward loading. And the area of this 125 multiplied by 6 would be 150. 150 minus plus 150 would be 0. So here is my shear diagram. It's going to reach to 0, which is correct. Now for calculation of bending moment diagram, we're going to say we have to drive the calculate the area for each one. And don't forget, we again have concentrated moment from the reaction point A. So because it's counterclockwise, it's minus. So from minus 2700 we start, then we add 225 by linear change to reach point B. So we're gonna reach to minus 1350. The calculation of area, which is 225 multiplied by 6, and we're gonna reach to minus 1350. And from here, point B, to reach to the point C, we have a straight line, so it would be again linear, and we add A2. It's all positive. So it would be something like this from here to here, and we're gonna reach to minus 450. Now at point C, to reach point D, at point D we have to reach to 0 because there is no concentrated moment and there is no support. Moment definitely is 0. We have to add A3 to this value. So we add it. The area is 6 multiplied by 150, and that's what we have to calculate divided by 2, and the answer plus this value. Now it's decreasing because it's 150, it reached to 0, so because it's decreasing, it should be decremental, so it would be something like this. That's what we can say about this, and we calculate this area, this is gonna reach to 0. The next one would be it's a pin at point C in this beam, and roller at D and fix at point A with this sort of loading. Now, first we have to drive the reactions. It's very important to know how to drive the reactions because we have one reaction here and we have one moment here. And after calculation, it would be 540 and it's 80. The best way for calculating these sort of questions, because we have 1, 2, 3 unknowns, it might be a little bit difficult, but this hinge help you to detach this structure from the right side. So the best way would be like this. When we detach, definitely this shear and this axial force at point C remain, and we just deal with the rest. It's MA and it's AY, and we can take moment around point C, sigma m around C equal to 0. So from here we're going to say AY multiplied by arm, this force multiplied by arm plus MA 0, and it helps to write one equation for this. On the other side, we can say that the right side, we're gonna give us another equation which we have concentrated load similar to this one we're gonna have with different direction of the load. It's QC, VC, but it's downward, it's on the left direction. And dy, if we write sigma m around C0 again, but from here it will be force multiplied by arm, concentrated load of 10 multiplied by arm, it gives dy. So we're gonna drive dy, and we can add another sigma fy0, and by two equations and 2 unknowns, we can drive ay and ma. Now we already derived it, and just the goal is just concentration on shear diagram and bending moment diagram. That's why I don't go through detail here. For the shear diagram, as I said, it's 80, go upward, it's upward, no load between A and B, so a straight line downward, total 115, so it's 18, 115, we just deduct it, and we're gonna reach to 35 minus 35. So it should be almost here, right? It's right. So from here, there is no load between B and C. I keep continue to reach point C, and after that, we're gonna see we have a concentrated load to reach to the point D. So because it's downward, so it's downward, it's straight, it should be linear. How much? 10 multiplied by 9, which would be 90, and we add 90 to minus 35 is here, and 90 minus 125 is here. Then after that, we have concentrated reaction here, which we drive the reaction here. For my calculation, it's 245. So we're gonna switch, as it says, go up and go up, and add this much, and I'm gonna reach to 120. Then it's going downward, so it tells me I have to go down. It's a straight line, it should be linear. I have to reach to point 0 at E, because if you have no reaction here, and the area of this one is 10 multiplied by 12, which is 120, minus plus 120 would be 0. So my calculation is correct. Now go for calculation of bending moment diagram. Don't forget we have concentrated moment for this case, which is counterclockwise. So it would be minus 540. Then from here, I go further from A to B. I calculate A1, which is 80 multiplied by 12. I calculate A2, don't forget it's minus, it's A3, it's positive A4. So it's a straight line. Oh, we have minus. From here, a straight line, from here, I go straight to reach to some point almost here. Then I would be able to say 80 multiplied by 12. It would be 420, as I see here in my calculation. So it should be, it's not true, it's this one. 420 is here, a straight line. Then minus A2, which is minus 35 multiplied by 12. At point C, there is one hint for this question. When we have the hinge, definitely moment is 0. So I have to reach to 0. It's a straight line, so it should be minus, because the area is minus, and it's straight line, so it should be or linear to reach 0. If this area plus this numerical is not 0, my calculation is wrong, because we have hinge, and hinge means there is no moment at this point. Now, after that, we have minus area of this trapezoidal. I calculated it's linear, so it would be to the order 2. It's a quadratic formula. Now, absolute of 35 to absolute of 125, it means it's increasing. So my graph would be to the order 2, but it's incrementally. So it would be something like this. You see the angle is increasing. Compare these two theta, it's increasing. And after that, I have to add area number 4, which is 120 multiplied by this length divided by 2. And here it's from 120 to 0, it's decreasing. So the graph should be decreasing decrementally like this. And you see the difference. So the moment here is like this, and we have no moment here. It's true at point E. It shows that it proves that my calculation is correct. The next example is for the application of the best way is to do superposition, but for this case, I just concentrate on regular method, and shear diagram would be here. I assume that it's symmetric, and you know that how to calculate that, but it's 55, the reactions. And we're going to say that at this point, because we have concentrated of 10K downward, so I have to go downward. How much? 10 minus. And after that, it will be distributed load downward, so it tells me go downward. It's a straight line. For the shear would be order 1, like this. And after that, we have concentrated load of concentrated reaction. Actually, it's not external load. It's 55 going upward. There's a jump here, and minus 10 after that here, and this value is minus 25, and this value here is minus 25 plus 55, this range, it's gonna reach to 30. And here, after 30, we're gonna have downward, a straight line would be to the order 1, so we're gonna draw line from here to here. And at this point, again, it's going to go upward. How much? 55. And we're gonna go up 55, and we're gonna reach to 25 as I drive. And again, it says downward, a straight line should be changed to order 1, and linear dropping down a little bit. Then it tells me go down. How much? 10. So you see it's very similar to the right procedure because it started from 0 and it's reaching to the 0. It's correct. Now I'm gonna go for calculation of bending moment diagram, and you know, calculation of area is the answer. From first I have to check, is there any concentrated moment? Fortunately we have no concentrated moment here, so we have no concern, and start from 0 and then add the area 1, which is minus, then area 2, which is plus, area 3, which is minus, and area 4, which is plus. This is all accumulative calculation for whatever we do for the moment diagram. It starts from 0, then minus A1. Because it's linear order 1, it will be linear order 2 for the moment. And it's from 10 to 25, the absolutes. So it's increasing. The graph would be something like this. Then after that, we add A2 to this value. It's from 30 to 0, so it's decreasing. And we're gonna reach to the maximum because at this point we have concentrated, we have a zero shear. And it's exactly in the middle because it's symmetrical, and this length should be equal to this length. However, in my drawing is not showing that. And from here, I have to reach to the maximum. It's decreasing. Order 1 should be switched to order 2 for the moment. So it will be something like this. And after that, I have to deduct area number 3. So to calculate this area, it would be 62.5, and decrease this value, and it gets back down, and my calculation shows I have to reach minus 87.5. So I have to draw something like this. Now I have to add A4, and this trapezoidal calculation tells me it's equal to 87.5. Fortunately, this one plus this one would be 0 when I add them up together. And it's from 25 to 10, so it's decreasing. When it's decreasing, my graph would be something like this. Because I started from 0 and reached to 0, it's a proof of my right calculation. The next example would be such a beam. So we have to derive the reactions, which 31.83, and this one is 21.17. In this case, it's overhang from two sides, and we have concentrated load here. For the shear diagram, it's going downward, so I have to go down, follow that, -8. There is no load in between, straight. Concentrated goes up to 31.87 should be added to this one, so we're gonna reach to 31.87. And then from here to here, it's distributed load downward, straight, so it will be to the linear, change to the linear, and downward, how much? 1.5 multiplied by 30, and we're gonna reach to here would be -21.17. Then 21.17 upward, and there is no other load here, so it shows that my calculation is correct. Now for the bending moment diagram, it's very simple, and you know that you have to derive the areas. This area is -80, and this area is 189.3. This is -149.3. Don't forget we have concentrated moment here, and now we have to consider this concentrated moment in my bending moment diagram. For here, I start from 0 because there is no concentrated moment here. At point A, it's straight, so it should be linear. It's minus, so going down. Then I have to add up 189.3. It's order 1, I have to make it order 2. Add it to this one, so it would be something like this. Don't forget, here we have 0 shear, so it's definitely my maximum moment. That's the maximum moment here at point, let's say E, and this is my point E. And when we add them up, the answer is 109.3, and after that we deduct minus 149.3, and we're gonna reach to point C, which is minus 40. Then after that, there is no moment here. So we keep continue at the same level as E's, because moment diagram is a cumulative calculation of areas. So the accumulated value so far is minus 40, and we keep continue up to reach to the end, and we have positive 40 from minus plus gonna reach to 0. It shows that my calculation is correct as well. In such example, we have cantilever beam, and we have two types of uniform distributed load. The reaction for this case shows that Cy is equal to 30 kilonewton, and the moment is in this case is minus 42, so it's in this direction. We have one concentrated moment as well, so we have to draw the shear diagram first. We start from the left. We start from A. At point A, there is no reaction, 0. It's linear, so it would be order 2. It's increasing from 0 to 8. So as long as it's increasing, we have to draw some incremental, but it's downward, so we have to make it to the order 2 downward. It's increasing. See, the theta is increasing. Now I'm gonna reach the point B, and from B to the C, we have downward again, so we have to go down. A straight would be changed to the order 2. Sorry, a straight would be changed to the linear. So from B to C would be something like this. And how much would be added to B is 8 multiplied by 3. Then at this point we have 30, and if you calculate, it's minus 30, and we add minus 30 plus 30, so we're going to reach to 0, which shows that my calculation is correct. B at the point B is minus 6. Now we have to drive bending moment diagram. Don't forget, we have concentrated moment here, and here we have the reaction at the point C. For this one, we have 15, which is positive, so we start from 15, and after that we calculate this area, and I call it A1, then calculate A2. All of them are minus. From here to here, it's to the order 2, so it will be to the order 3, and it's from 0 to 6, absolute value is 6, so it's increasing. So we have to drive something increasing in the curve, and we have to do area of this one. Here is something like this. so order 3. Then at this point, from this point, which is point B, and to point C, we have to add again minus area 2. We have to drive this area, which is trapezoidal, and it's linear, so it would be to the order 2. It would be something like this. And this is, after calculation, is minus 42. I'll calculate this area, and at that point is, point A is 12. Now, minus 14, we have plus 14 as well, 42, minus 42 plus 42, which we're going to reach to 0. So from here to here. So you see that we started from here, 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 from 0 to 0. It shows that my calculation and my graph is correct. The last question is about overhang beam with the concentrated moment. After calculation, we're going to see the reaction is 8 downward. Let me show this way, and upward 47. So we follow the same previous procedure, shear diagram, and we're going to say start from point A downward, so we go down 15 because of this concentrated load, no load in between, then 47 to the up direction, minus 14 added 47 gives 32. Then downward, a straight line would be switched to linear up to this point. 6 multiplied by 4 is 24, deducted from 32, and we're going to reach to 8. And it says go down to the amount of 8, and reach to 0. So 0 to point 0, which shows my drawing calculation is correct. Then bending moment diagram. Don't forget we have concentrated moment here, so it's minus. We have to go minus 20 first, then add this area, which is minus, and add A2, which is positive in the upside of this graph. Minus A1, we have to calculate this area, add minus 20 to this 1, and it's straight, so it would be to the change to the linear to reach to the point B, which is minus 80. Then add A2 to reach to the point C, and it's to the order 1, it's linear, it would be order 2. It's decreasing because 32 reached to point 8. It would be something like this. It reached from 0 to 0, so it shows my calculation is correct. That's all about it.